Hey guys, so today we're going to get back into the 8080 assembly stuff, and we have done ATOI, which is, it's not the best ATOI, it's like a 3 character ATOI. But today we're going to do ITOA, the reverse, so we can do ASCII to integer, and now we're going to turn the integers back into ASCII. And the best part about this function is that this is the correct way to do it. This will use something called Double Dabble. And the Double Dabble algorithm, I'm not quite sure exactly how it works. It just does. Basically, the idea is this. You take a base 2 number, and then you turn it into a base 10 number. And a base 10 number is very easy to divide by 10. You just shift the entire thing down by 1. And that's pretty much what you do when you write your own I2A function, is you divide by 10, see what the modulo is, and turn that into ASCII by adding 48 or 0, ASCII 0. And then you store that number somewhere, you increment counters, and you loop until you're done. That's exactly what this does. There's a lot of loops in this. I'm not sure if this is the most efficient way to do it. This is a way to do it, and I don't care about efficiency quite yet. If anyone has any other idea of how to do I2A and ATOI very efficiently and very agnostically in 8080 assembly, please let me know. But here we go. First, we're gonna do the regular boilerplate. You're gonna do right. You're gonna do right I2A and right assembly, and then get us of course equal to 5. Print is gonna be equal to 9. Yep. And now we're going to do our defines here. So your int size is going to be 4, right? Number of bytes in int. So I want to do a 4-byte integer. You can do any size integer. You can do 2-byte, 4-byte. You can do 8-byte. Doesn't matter. And then you want to do the ITOA bit size, right? How many bits is that? So that's going to be int size times 8, right? Number of bits. Okay. You don't need this one. You'll see, like you can just do that inline if you really want to. Then we're going to do sorry, I have my stuff right here. You're going to do your BCD size. Your BCD size is going to be the number of BCD bytes. So you have your binary number. Now you want to turn it into binary coded decimal. So to do a 10-digit number, you only need 5 bytes because each nibble is one of the digits, right? So, right, BCD storage size. So this will be inherent to the ITOA function. If you add this in, you'll have to have a BCD size somewhere. And then you want to do your ASCII size. And this is going to be 10 because 10 digits, it'll be expanded into 10 bytes, right? And then ASCII size is turned into text. And this will be different depending on your use case. So you might not need 10 digits when you're doing a 2-byte integer instead of a 4-byte integer. Stuff like that. And we're done. And then we do the generic starting at 100 start. So now what I want to do is finish the boilerplate. I'm not going to cut this. This is just annoying. Bin num, right? What is bin num? Bin num is going to be the number that we are going to turn from binary from integer into ASCII. And I want to do 1, 2, 3, 4, 5, 6, 7, 8 H. So you would think you do 12H, 34H, 56H, and 78H. But that's not the case because we will be doing least significant byte first. So we actually have to move things around. So things like this. There. So now we have 78, 56, 34, 12. You have the least significant byte first. That's just how the 8080 generally does. You can change this if you want, but just to keep with the addressing, let's just keep it this way. Right, if you change the number, then you're going to have to change the loops in this program, but it's up to you. I'm not going to tell you how to make your own ITOA function. Then you need your ITOA BCD. And this is going to be BCD size. Right, so this is going to be placeholder for bin to BCD, right? So you're going to turn this into BCD encoded decimal, which is going to be up to 5 bytes in total size because that way you have 10 nibbles. Now, this is going to be your actual string. So this will be your string location. ASCII num. I'm just calling it that because, you know, why not? Yes, and then ASCII, it'll be ASCII size, right? So ASCII variable placeholder, okay. And of course you need to end your strings in a $sign if you're using the built-in print function, which we will be using because we're going to use the putS. VIC print call bdos return, and there you go. Okay, I think that's the boilerplate. Now, let's get down to brass tacks here. So the first thing we're going to do, and you don't have to do this, is we're going to zero out the BCD, we're going to zero out the I2A BCD. This will prevent you from seeing weird text when you convert it from BCD to ASCII. It's not inherently part of the I2A function, but if you don't want, whatever, you can just set them to 0. You don't have to, it doesn't have to be programmatically set. In fact, you know what? Let's do it. No, I can't do it because this is a variable. This is a defined, so we're just going to set it. So let's just do it, right? So LXI H right ITOA BCD, and then MVI B BCD size. So this will be the counter. And then, I copied this. By the way, I copied this program from a site online. MVI 0. We're gonna write load 0, and then of course you want to increment H. Decrement your counter, and then JNZ I loop, right, continue till done. Boom, that's just the memset. This is just a memset. ITOA, BCD, 2 zeros. Boom, okay, done. Now, we're going to set up bit counter. The bit counter is going to be this. It's going to be MVI B ITOA bit size. Okay. And then C loop. So I have C loop, an R loop, and B loop. These are just They're just names of loops, man. Again, I just copied this from a place online, so don't worry about it. C loop. What is this? This will be doing. I have this written out for me. Right. Initialize a left shift for a binary number. Okay, so it's going to be backward, right? You're doing things the reverse way. LXI bit then num. Yeah, let's fix that. Okay. And then we're going to see int size. Okay, so that's going to be another counter here. Set up byte counter. Okay. And then this is going to zero out carry. When you set it to 0, or like when you not when you set it to 0, but when you set the accumulator to 0 through an arithmetic function, there you go, then you clear the carry. Now, this will be our loop, and our loop will right shift binary number, 1 place left, leave no significant bit in carry. Okay, so our loop, this will be move what's in HL to A, rotate left through carry. Okay, move accumulator back to where HL is pointing, increment HL, and then decrement the byte counter. Yep. And then J and Z, our loop, right, loop till done. Okay. Now we're going to basically, this is where things get a little too voodoo-y for me. I'm not really quite sure what's going on. It says initialize to double the BCD result register contents by performing a multiple precision BCD add. This is part of the double dabble algorithm I just don't understand. I understand the concept of it, but please, if someone can explain it like I'm 5, please put it down below. Initialize double the BCD result register contents by performing a multiple precision BCD add. So you have to basically have to turn the whole node into BCD. We will see. So LXI H ITOA BCD. So right, point at BCD result placeholder, right? Okay, and then MVI C. And then you got to set the byte counter, right? So you got to set up BCD size. How big is it? Okay, cool. Now we do the loop. So double the result BCD, add in the carry bit. The loop. So first we're going to move, right, M to A, leave HL to A, Okay. ADC, and then we're going to ADCM. Okay. DAA. Right. Convert to BCD. And then we're going to move the accumulator back to HL, increment HL, decrement counter, GNZ D loop, right? Loop till done. Okay. And then test to see if all bits have been shifted. Right? If not, return to the main loop. So DCR B. Remember, B is the 32. B is the 32 bit, or the bit size, right? And then JNZ C loop till done. Okay. And then finally we have the BC. Basically, we now have this turned into binary coded decimal is now stored here at ITOA BCD. Now, in order to print it, we have to turn it into ASCII. Okay. Let's do it. ASCII num plus ASCII size -1. I'm not quite sure about why the -1 is necessary. Basically, I have to point to the end of ASCII num, and I'm going to decrement backward because it's just the way this works. It will. The BCD is flipped, right? So because this is flipped. And then I will LXI H ITOA BCD. Now HL will point to my binary coded decimal, and D will point to where I want to store it. And then MVI C BCD size. Now I want to do a loop for all the digits in there. Okay. And now my loop is going to be called ASCII loop. Move M to A. Right, move HL, move the contents of HL, or where HL is pointing, to the accumulator. Call comp byte, and comp byte is down here. I'll compare bytes. You'll see what I mean. Once I compare the byte, I'll move the contents of oh my god, one moment. I gotcha. Don't worry about it. You'll see what I mean. Next, so basically what I have just I'll show you compare byte first. Compare byte goes like this. I'm going to take my binary encoded decimal byte. Say it's 69, okay? 69H, but it's 69 decimal because that's binary encoded. What I'm going to do is I'm going to AND it with 0FH. So I'm going to just get the lower 4 bits, okay? Then I'm going to add ASCII 0 to it, or 48. So then I will turn that number into ASCII. Then I will store that number that's in A, store it to D. I will decrement D, because remember it goes backward, and then you return from the subroutine. Cool. So this right here will store the lower 4 bits of the accumulator. Okay, now I want to store the top 4 bits. Well, how do I do that? Well, unfortunately, there isn't a shift, but there is a rotate, and unfortunately, I have to rotate 4 times. RRC, 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 RRC. Okay, rotate through carry. And then call comp byte. For some reason, I tried not anding FH to this number, and I just get garbage, complete garbage in this digit. I have no idea why. Apparently RRC should just carry, like the carry shouldn't be rotated into the accumulator. I thought this would just work. It's like in C, you just shift things over and it just works. But apparently I have to AND it with the 0FH again to work. Please, if anyone knows why this is, please let me know down below. Next, I will increment my HL pointer. I will decrement the C counter, and I will jump until done. Okay, and then print print ASCII num. LXI D ASCII num. I'll put as okay, now let's see if this works. Of course not. I swear to God. Please, if you speak of this to anyone, I will hunt you and I will find you. Okay, so now let us check our work. We have 03051. Sorry, 5419896. And let's do this. 1, 2, 3, 4, 5, 6, 7, 8. And it looks like the numbers match up. Look at that. Right here. I have the same number here as I have in my ITOA function. Of course, there is leading zeros. You can get rid of them. For this purpose, for the purposes of this video, I will not be doing that. I don't think it's worth it, but you do you. Anyway, that is it for this video. This is finally ITOA. I have ATOI, kinda. I want to make it better, but now I have a working ITOA, which will work with any byte size. And yeah, I mean, into hex, hex to ASCII. This will all be really good. This will all be easy. I would like to explore floating point numbers in 8080 assembly, that's something else entirely. We'll cross that bridge when we need to, but right now I don't need to. But I'm glad I now have it working. ITOA routine, and please feel free to use it. And I will see you next time when I have something else cool to show you in 88 assembly. See ya.